Great. I finished that video. This video. Day 2. Okay. So we talked about net forces acting on things, or not net forces, but the different types of forces. We looked at a free body diagram. We have a few other ones to look at as well. Because the problem is not everything's a car driving along the road. I'm going to turn this so I can see what's going on. Some things are an egg falling from bleachers, right? So if we have an egg falling, that was a terrible egg. We have gravity acting on it, pulling it down. So we're looking at different examples of free body diagrams. That's what we're doing. Kind of skip that part. Important. Free body diagrams, what they look like. What forces act on eggs falling? Just force of gravity. And then there's always a force of friction, or it's going to be the force of air. Resistance, it's friction. It's fluid friction. That's all it is that is acting on there. But if we're dropping it and it's falling, there's no horizontal forces acting on, just gravity and air resistance. Let's look at something else. Let's have a cat. If that cat is laying down on the ground, there's still the force of gravity acting on it because it's on Earth. Because it's laying down, there's also a normal force acting on it, but if it's just laying there, it's not, anything else acting on it. Let's have another example of different things we can see. We still have a force of gravity, our normal force. Let's have something on a frictionless world. We would have our force applied. We can't really have a frictionless world. That's just silly. Because the whole unit is for friction. This is a car, something driving, something being pushed. Right, we can have our force applied. If it's on the ground, we have gravity, and then the normal force, force applied, and force of friction acting on it. These are really our free body diagrams we're going to see. Oh, we have another one. Not all of these. I have room over here. Let's do a person on a swing. The G. What's acting, if you're sitting on a swing, you're not moving, we're just sitting, making it easier on ourselves. We have the force of gravity acting on them. There's also 2 lines going up. This is the force of tension. So these are like it's the ropes on the swing, or the chain. So we have force of gravity, and then we have force of tension. If we have ropes or some chain, something like that, we get tension on there instead of like a normal force, because this person would be off the ground, but they need something. But what this really is, it's not really any different than like a normal force, right? Because if our swing set comes down like this, our person's weight is right here, distributed on all 4 of these. So our force of gravity really isn't there. It's on the legs of the swing set. And then up here we would have our normal force. So really our force of tension is equal to like our normal force. That's what I'm trying to get at with my drawing here of we end up with the force of gravity really being over on these posts, and our force of tension is really equal to our normal force. But that's not how a free body diagram looks. It's just kind of like the real world, how it actually looks. So these don't belong on a free body diagram. We stick with our force of tension and our F, G. I just wanted to explain where the tension goes, because it has to go somewhere. But eventually it's back down and is equal to the normal force. So if you have 100 newtons being pulled down, each rope should be feeling 50 newtons, right? Two of them there. Okay. Now I think we got all our force diagrams. We want to look at one other thing. Just erase diagrams, and I'm going to add one back on. Let's label these really quick. Okay, we're going to look at something called the net force. We'll put net force. It's the sum of all forces acting on an object. That's going to determine the direction its movement is, or acceleration is. If R if this is a car, right, we may have, let's do 1,000 newtons here, and 1,000 newtons here. Because they're opposite of each other, they cancel each other out. Who cares, right? Our force applied, let's say we're at a stop sign and then you push the accelerator, the gas, and it applies a 100 newtons of force. It's probably much bigger than that, but that's going to work. And the friction force your tires feel is 10 newtons. So our net force acting on this car would be, would be 90 newtons to the right. So that's just really what we're doing with our net force, is which direction are we moving, or accelerating, and you're just adding these up. And if they're opposites, these really could be negatives then, or maybe they should be negatives. So like this is now an addition problem versus a subtraction problem. You're smart people, you can figure out if they're going opposite directions, they should cancel each other out, right? So we could put negatives in there though. That's what I wanted to get at. If we switch this around, so now we take our, press less on their accelerator and we apply more brake. Now our brake is at 100 newtons. So our friction is increased while we don't really have any gas on there. Let's take our foot off the gas, because you shouldn't be pushing on the gas and applying a brake. That's just weird. What would be our net force on this? Opposites cancel. This one's 0. So our net force should be like left friction force 100 newtons. So if we wanted to find like the deceleration of our car here, if we knew the mass of it, let's find the mass of our car, which is probably going to be more like the mass of a person on a bike. I'm going to solve for the mass. We know Fg equals mg. We know this is 1,000 newtons. We don't know mass, but we know 9.8 meters per second squared for the acceleration of gravity. Right, divide by 9.8. So mass is equal to 1,000 divided by 9.8, giving me 102 kilograms. That's close enough. So if I want to find my deceleration, I'm going to plug it in the same F equals ma. I'm going to put my force of friction, mass, and acceleration, the deceleration part. I know my force of friction is 100 newtons. I know my mass, that's the 102 kilograms. I don't know the acceleration. I'm solving for that, right? So divide by 102 on both sides. So we end up with 100 divided by 102, giving me 9.8, or 0.98 meters per second squared. Since it's a deceleration, I'm going to put a negative there because I know it should be negative or slowing us down from our speed. So that would be how we'd find like a deceleration with our net force. And how to find a net force. Different types of free body diagrams. I hope that was everything that we needed to cover in the videos. It's hard when someone interrupts and then you have to do it over 2 days.